Have you ever looked at a graph and wondered, is there a way to find the area under the curve? Well, if so, the answer to your question is one of the most elementary definitions of the integral. This is the integral operation, and here's how it works. Let's call this function on the graph f of x. Now, to use the integral operation, we're going to choose an x value of where we want to start calculating the area. And then, we're going to pick another x value of where we want to stop calculating the area. In this example, I chose a to be my starting value and b to be my ending value. In this example, a and b are both x values. To write our integral, we're going to place our starting x value at the bottom, and then our ending x value at the top. Then, inside the integral, we're going to put the function that we want to find the area of. In this case, it's the function f of x. The last step is choosing the variable of respect to. This just means you're only considering x as a variable. Now that we've written out our integrals, we are able to find the area between the x values a and b. The area under the curve was 46 blocks of TNT. Before we go over more uses for the integral, let's go over how the integral actually works. So, for this demonstration, I made a slightly bigger graph. So, how does the integral find the area under the curve? The integral starts off with estimating the area under the curve. You see, in the real world, we're not able to find the area under a complicated curve such as this one. Well, not with basic geometry at least. So what mathematicians have done is estimated the area by using rectangles. So here I built some rectangles to demonstrate this. Each rectangle has a width of 4 blocks, and the heights are dependent on the leftmost block. Now, take a look at the result. The area comes out to be 1088 blocks. Remember that this is still an estimation, and that's why there's so much unaccounted area. Now what I've done is I've estimated the area under the curve using rectangles that have a width of 2 blocks, and the heights are still dependent on the leftmost block. Also, notice how since I'm using rectangles that have a width of 2 blocks, I'm able to add more rectangles. Using rectangles that had a width of 2 blocks, the new estimation of the area under the curve is 1132 blocks. Now, what I want you to notice is that the smaller the rectangles get, and the more rectangles I add, the better the estimation gets. Once mathematicians realized this, they came to the conclusion that if they were to make an infinite amount of rectangles, their estimation would turn into the real answer. Here is a demonstration that's not in Minecraft. You can see we start off with 3 different rectangles, and this is our starting estimation. And as we keep adding rectangles, our estimation gets better and better, until our estimation is almost perfect. So, if we kept adding rectangles infinitely, that means our estimation would be the perfect answer. Now, going back to Minecraft, our perfect answer was 1157 blocks. Now that we've gone over how the integral works, let's go over some applications that we can use it for. One of the most important applications of the integral is solving motion problems. What better way is there to demonstrate this than by using a car in motion? In this example, I'm driving my car at a nonlinear velocity. This just means my acceleration changes throughout my drive. Since my acceleration is changing, it is hard to determine how far I've gone in a certain amount of time. This is where calculus comes into play. First, I will have to gather some information about my velocity at different times throughout my drive. At 1 second, I'm going 36 meters per second. At 2 seconds, I'm going 49 meters per second. At 3 seconds, I'm going 64 meters per second. Here is a velocity versus time graph that represents my velocity at select times. Using this graph, we can make a model that represents our velocity as a function of time. This is the function that is being used to model our velocity. By taking the integral, or the area under the curve of this function, we are able to find my displacement in the first 3 seconds. This is because the area under the curve of a velocity graph is displacement. Now, let's break down how we actually calculate this. First, we set up our integral of our velocity function from time 0 to time 3. Then, we plug it into a calculator, or we do it by hand. This result will give us the displacement I've traveled in the first 3 seconds. From our result, you can see that I've traveled 129 meters in the first 3 seconds. Now let's talk about why the area under a velocity versus time graph gives you displacement. Here I've tried to replicate my graph from the problem. Going back to how the integral calculates the area under a curve, an infinite amount of rectangles are used. Well, if we take one of those rectangles and find the area of one rectangle, you will see why the area gives you displacement. To find the area of a rectangle, we are going to use base times height. In this case, let's say the rectangle has a base of 2 blocks and a height of 4 blocks. Now you have to remember that this is a velocity versus time graph, which means our x and y axes have units attached to them. When there's units attached to the axes, you have to include them when you're calculating the area. So in this case, to find the area of this rectangle, we would do 2 seconds times 4 meters per second. And when multiplying units, you have to treat them like numbers. So in this case, our seconds would cancel out, leaving us with 8 meters. This is why, since the integral is basically a bunch of rectangles, the area of those rectangles will give you units in meters, which represents displacement. So to summarize, the integral can be used to find the area under the curve of a function. It can also be used to find the displacement of an object given that you have a velocity versus time graph.